Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Maybe the day has been long and restless, or perhaps you're the kind of person who finds comfort in gentle knowledge rather than racing thoughts. Either way, you've come to the right place. Tonight, we're exploring something that touches every moment of your life, yet often goes unnoticed in its quiet beauty. The weather, not the dramatic storms or fierce winds that capture headlines, but the soft, subtle, and deeply peaceful truths about the atmosphere that surrounds you. Let your shoulders drop, your breathing slow, and your mind settle like morning mist on still water. Because tonight, we're drifting through clouds, riding invisible currents, and discovering the gentle secrets hidden in every breath of air. Some of what you hear may surprise you. Other facts might simply float by like snowflakes on a winter evening, delicate and quietly unforgettable. If these calm explorations bring you peace or help you find your way to sleep, consider liking and subscribing. It helps others discover this sanctuary of gentle learning, one peaceful soul at a time. Now let yourself get comfortable, and let's begin this soothing journey through the quiet wonders of weather. Snowflakes are never truly identical, but they follow hidden patterns. Each snowflake that falls from the sky is a tiny miracle of crystalline architecture, formed in the dancing chaos of clouds high above. While it's true that no two snowflakes are exactly alike, they all follow the same fundamental rules of physics and chemistry. As water vapor condenses around microscopic particles of dust or pollen, it begins to freeze in hexagonal patterns, always six-sided, always symmetrical. The journey each flake takes through different temperatures and humidity levels shapes its final form. Some grow delicate dendrites, others form simple plates or columns. The variety is endless, yet each one obeys the same gentle laws of nature. In the quiet descent from cloud to earth, every snowflake is both unique and part of a universal pattern, like individual notes in an infinite, silent symphony. Clouds are mostly empty space filled with floating water. When you look up at a fluffy white cloud drifting peacefully across the sky, you're seeing something that's almost entirely empty. Those seemingly solid masses are actually composed of billions of tiny water droplets, each one so small that a teaspoon of cloud might contain only a few grams of actual water. The droplets are suspended in air, floating on invisible currents, held aloft by the gentle balance between gravity pulling down and air pressure pushing up. A single cumulus cloud, the kind that looks like cotton balls on a summer day, might weigh as much as several elephants, yet it floats effortlessly through the atmosphere. The spaces between the droplets are vast on a molecular scale, filled with the same air you breathe, saint thinner and cooler. Clouds are poetry written in water and air, substantial yet ethereal, heavy yet weightless. The air pressure around you is constantly changing, like a slow, invisible tide. Right now, as you rest, the atmosphere above you is pressing down with the weight of an entire column of air stretching from where you are to the edge of space. This pressure rises and falls throughout the day in gentle, predictable rhythms. When a high-pressure system moves in, the air becomes denser, often bringing clear skies and calm weather. Low-pressure systems create the opposite effect, allowing air to rise and often forming clouds and precipitation. These pressure changes are so gradual that your body adapts without you noticing, though some people can sense approaching weather through subtle changes in how they feel. The atmosphere breathes around you in slow, massive waves, invisible tides of air that T-shape every weather pattern you experience. Rain begins its journey in the darkness of clouds. Every raindrop that touches your skin or taps against your window has traveled an extraordinary path through the sky. It starts as invisible water vapor, rising from oceans, lakes, and rivers, lifted by the warmth of the sun into the cooler heights of the atmosphere. There, in the heart of clouds, water vapor condenses around tiny particles, forming droplets so small they can float on air currents. These droplets grow by colliding and merging with others, becoming heavier and heavier until gravity finally wins the gentle struggle. The largest raindrops are only about 5 millimeters across before they break apart in their fall. Each drop is a perfect sphere, shaped by surface tension into the most efficient form for its journey earthward. Rain is the sky's way of returning borrowed water, completing a cycle that has continued for billions of years. Wind is simply air trying to find balance. The gentle breeze that moves through your hair or rustles leaves outside your window exists because the atmosphere is constantly seeking equilibrium. When the sun heats different parts of the earth unevenly, it creates areas of varying air pressure and temperature. Warm air rises, cool air sinks, and in between these movements, wind is born. The rotation of the earth adds its own twist, literally, creating the spiraling patterns we see in weather systems. What feels like a random gust or a steady flow is actually part of vast, interconnected currents that circle the globe. Trade winds, jet streams, and local breezes are all expressions of the same fundamental principle. Air moving from areas of high pressure to low pressure, seeking the calm of balance that never quite arrives. Fog is simply a cloud that has touched the ground. On misty mornings when the world seems wrapped in soft gray cotton, you're actually walking through the bottom of a cloud. Fog forms when the air near the ground becomes saturated with moisture, usually when warm, moist air meets cooler surfaces or when cool air moves over warmer water or wet ground. The tiny water droplets that make up fog are identical to those in clouds high above, just formed closer to Earth. Fog can be so thin it barely dims the sunlight, or so thick it reduces visibility to just a few feet. In coastal areas, fog often rolls in from the ocean like a slow, silent tide, bringing coolness and mystery to the landscape. It transforms familiar places into dreamscapes, softening edges and muffling sounds, creating a world that feels both intimate and infinite. Lightning creates its own weather in the split second it exists. When lightning flashes across the sky, it doesn't just illuminate the darkness. It briefly creates conditions more extreme than those on the surface of the sun. The electrical discharge heats the air in its path to temperatures of about 30,000 degrees Celsius, roughly 5 times hotter than the sun's surface. This instant heating causes the air to expand explosively, creating the thunder we hear moments later. The entire process, from the initial buildup of electrical charge in storm clouds to the final crack of thunder, is one of nature's most efficient ways of balancing electrical differences in the atmosphere. Lightning is the atmosphere's way of releasing tension, a sudden, brilliant discharge that restores equilibrium to the electric fields building in storm clouds. The atmosphere has layers like a gentle, invisible cake. Above your head, the air doesn't just fade gradually into space. Instead, it's organized into distinct layers, each with its own characteristics and personality. The troposphere, where all weather occurs, extends about 12 kilometers up and contains most of the atmosphere's mass. Above that lies the stratosphere, home to the ozone layer that protects us from harmful solar radiation. Higher still are the mesosphere and thermosphere, where the air becomes so thin that meteors burn up in brilliant streaks. Each layer has its own temperature patterns, wind currents, and role in the grand circulation of the atmosphere. It's like living at the bottom of a layered ocean of air, each level contributing to the weather patterns that shape your daily experience. Humidity is invisible water dancing in the air around you. The air you breathe right now contains water, not as droplets you can see, but as individual molecules of water vapor mixed invisibly with nitrogen and oxygen. This hidden moisture rises from every body of water, every leaf on every tree, and even from your own breath. When meteorologists talk about relative humidity, they're describing how much water vapor the air is holding compared to how much it could hold at that temperature. Warm air can carry more moisture than cool air, which is why humid summer days feel so heavy and why your breath becomes visible on cold mornings. The water in the air is constantly moving, evaporating from surfaces, condensing into droplets, and joining the endless circulation between earth and sky. Barometric pressure changes can influence how you feel. The weight of the atmosphere pressing down on you isn't constant. It rises and falls in subtle patterns that your body can sometimes detect. Some people report feeling changes in their mood, energy levels, or physical comfort when weather systems approach, particularly when air pressure drops before storms. While the mechanisms aren't fully understood, it's thought that pressure changes might affect fluid levels in your inner ear or influence the way your joints and tissues respond to the surrounding environment. The atmosphere isn't just around you. It's gently pressing against every surface of your body with a force of about 14 pounds per square inch. When that pressure changes, even slightly, some people can feel it like a whisper from the approaching weather. Dew forms in the quiet hours when the world sleeps. In the stillness before dawn, when temperatures drop to their lowest point, something magical happens on grass, flowers, and spiderwebs. Water vapor in the air condenses directly onto cool surfaces, forming tiny, perfect droplets of dew. This process requires clear skies and calm air, conditions that usually occur during peaceful night hours. Each dewdrop is like a tiny lens, capturing and reflecting the early morning light. The formation of dew is actually the atmosphere's way of releasing excess moisture when the air becomes saturated at cooler temperatures. It's a gentle process, silent and gradual, turning invisible water vapor into visible pearls of moisture that glisten in the first light of day. Frost is winter's delicate artwork painted on cold surfaces. When temperatures drop below freezing and water vapor in the air comes into contact with cold surfaces, It doesn't form liquid droplets first. Instead, it transforms directly from vapor to ice crystals in a process called sublimation. This creates the intricate patterns of frost you see on windows, leaves, and car windshields on cold mornings. Each frost formation is unique, shaped by tiny variations in temperature, humidity, and surface texture. The crystals grow slowly, building elaborate structures that look like ferns, feathers, or abstract geometric patterns. Frost is nature's way of creating temporary art. Delicate ice sculptures that disappear with the first touch of sunlight or the slightest rise in temperature. The jet stream is a river of fast-moving air high above the clouds. About 10 kilometers above the Earth's surface, narrow bands of extremely fast-moving air circle the globe like invisible highways in the sky. These jet streams, typically moving from west to east, can reach speeds of over 300 kilometers per hour. They're created by the temperature differences between warm air masses from the tropics and cold air from polar regions. Commercial aircraft often ride these air currents to save fuel and reduce flight times, like boats following favorable ocean currents. The position and strength of jet streams influence weather patterns across entire continents, steering storm systems and affecting temperature patterns thousands of kilometers away. They're part of the atmosphere's grand circulation system, moving heat and moisture around the planet in patterns too large to see but powerful enough to shape the weather you experience. Every breath you take connects you to weather systems around the world. The oxygen molecules you're breathing right now have traveled incredible distances through the global circulation of the atmosphere. That same air might have been part of a cloud over the Pacific Ocean last week, or swirled through a forest in South America last month. The atmosphere mixes and moves constantly, carrying gases, moisture, and even microscopic particles on journeys that span continents. When you exhale, the carbon dioxide you release joins this global circulation, potentially becoming part of a plant's photosynthesis process thousands of kilometers away. Breathing isn't just a personal biological process. It's your direct connection to the vast, dynamic system of air that surrounds the entire planet. Temperature gradients create invisible architecture in the atmosphere. The air around you isn't uniformly warm or cold. It exists in layers and pockets of different temperatures that create invisible structures affecting how weather develops. These temperature differences drive convection currents, the rising and sinking motions of air that form clouds, create wind patterns, and distribute heat throughout the atmosphere. On a sunny day, the air just above a paved road shimmers because hot air rising from the surface has a different density than the cooler air above it, bending light in visible ways. The same principle works on much larger scales, creating the thermal columns that birds use for effortless soaring and the updrafts that feed thunderstorms. Temperature differences are the engine that drives all weather, creating an ever-changing, three-dimensional landscape of moving air. Snow has a voice that changes with temperature. When you walk through fresh snow on a cold winter day, each step produces a distinctive sound that tells a story about the frozen crystals beneath your feet. At temperatures just below freezing, snow tends to be quiet, almost muffled, because the individual flakes are slightly sticky and compressed easily. But when temperatures drop well below zero, Snow becomes crisp and squeaky underfoot. This happens because the ice crystals become harder and more brittle, fracturing and grinding against each other with each step. The sound is actually thousands of tiny crystal fractures occurring simultaneously, creating that characteristic crunch that seems to echo in the still, cold air. Even snow speaks, though only in whispers and gentle crack that fade quickly into winter silence. Heat lightning is a gentle mirage of distant storms. On warm summer evenings, you might see faint flashes of light on the horizon, flickering silently against the darkening sky. This phenomenon, called heat lightning, isn't actually a special type of electrical discharge. It's simply regular lightning from thunderstorms so far away that the sound of thunder never reaches you. The lightning appears as soft, diffused flashes because it's being scattered and reflected by water droplets and particles in the air over great distances. What you're seeing is the light from storms that might be happening 50 or even 100 kilometers away. Their electrical displays dimmed and softened by the atmosphere into something almost dreamlike. It's nature's way of showing you distant drama without the intensity, like watching a storm through frosted glass. Ice crystals in clouds determine what falls from the sky. High in the cold reaches of clouds, the fate of precipitation is decided by microscopic ice crystals and supercooled water droplets existing in delicate suspension. When the temperature is just right, usually around -10 to 15 degrees Celsius, something fascinating happens. Ice crystals and water droplets coexist in the same cloud space, but the water molecules prefer to join the ice crystals rather than remain as liquid droplets. This process, called the Bergeron process, causes ice crystals to grow larger while water droplets shrink and eventually disappear. The growing crystals become heavy enough to fall, and depending on the temperatures they encounter on their journey down, they might remain as snow, melt into rain, or partially melt and refreeze into sleet. Every type of precipitation begins with this quiet dance between ice and water in the hidden depths of clouds. Thermals are invisible elevators in the atmosphere. On sunny days, the Earth's surface heats unevenly, creating columns of warm, rising air called thermals. These invisible currents spiral upward like gentle tornadoes of warm air, often reaching heights of several thousand meters. Birds have mastered the art of finding and riding these thermals, circling effortlessly upward without flapping their wings. Glider pilots use the same currents to stay aloft for hours, reading the landscape below for clues about where thermals might form. Dark pavement, bare soil, and rocky surfaces heat up more quickly than forests or bodies of water, creating the temperature differences that birth these rising currents. Thermals are the atmosphere's way of mixing and redistributing heat, creating invisible highways that connect the ground to the sky in columns of gently spiraling air. The smell of rain has a name and a story. That distinctive fresh scent that fills the air just before and during rainfall is called petrichor, from the Greek words for stone and the fluid of the gods. This pleasant aroma comes from oils produced by plants during dry periods, which are absorbed by clay-based soils and rocks. When rain falls, these oils are released into the air along with a chemical compound called geosmin, produced by soil bacteria. The combination creates that clean, earthy smell that many people find deeply satisfying and peaceful. It's one of the few weather phenomena that appeals directly to your sense of smell, a chemical signature that announces the arrival of precipitation and the renewal of the natural world. The scent of petrichor connects you to rainfall in a way that's immediate and primal, a reminder that weather isn't just something you see and feel, but something you can smell and taste. Atmospheric pressure waves can travel around the Earth multiple times. When large weather systems develop or major atmospheric disturbances occur, they can create pressure waves that move through the atmosphere like ripples on a pond. These waves travel at the speed of sound, about 340 meters per second, and can circle the entire planet several times before finally dissipating. The waves are usually too subtle for humans to detect directly, but sensitive barometric instruments can track them as they pass. Major volcanic eruptions, large explosions, and even some severe thunderstorms can generate these traveling pressure waves. It's as if the atmosphere has its own way of sharing news, sending gentle pulses of pressure changes around the world to announce significant events. These invisible messengers connect weather events across vast distances, creating a global communication network written in air pressure. Virga is rain that never reaches the ground. Sometimes, especially in dry climates, you can look up and see gray streaks extending from clouds toward the earth, like ghostly curtains hanging in the sky. This is virga, precipitation that evaporates completely before it can reach the surface. The rain or snow falls from clouds into the drier air below, where it gradually disappears, drawn back into the atmosphere as invisible water vapor. Virga often creates beautiful, ethereal displays, with wisps of precipitation creating patterns that shift and change as air currents move them. It's particularly common in desert regions, where the hot, dry air near the ground can evaporate falling precipitation very quickly. Virga is nature's way of trying to bring moisture to thirsty landscapes, even when conditions aren't quite right for the water to complete its journey. Stable air creates the calmest weather conditions. When the atmosphere is in a stable configuration, with cooler air near the ground and warmer air above, it resists vertical movement and creates some of the most peaceful weather you can experience. In stable air, clouds tend to form in flat, layered sheets rather than the towering, puffy, cumulus formations associated with unstable conditions. Winds are usually gentle and steady, and precipitation, if it occurs, tends to be light and steady rather than heavy and intermittent. These stable conditions often occur during high-pressure systems and can persist for days, creating those perfect weather days when the air feels calm and settled. It's during these periods that the atmosphere seems to rest, like a sleeping giant breathing slowly and peacefully. Ground fog forms through the quiet cooling of the earth. In the hours after sunset, when the day's heat radiates away into the clear sky above, the ground cools more quickly than the air just above it. If there's enough moisture in the air and the cooling is gradual and steady, fog begins to form in low-lying areas where cool, moist air settles. This radiation fog, as meteorologists call it, typically forms on clear, calm nights and often reaches its thickest point just before dawn. It creates a dreamy landscape where familiar places become mysterious and ethereal, with objects emerging from and disappearing into the gray veil. The fog usually dissipates shortly after sunrise, as the warming ground heats the air and reduces its relative humidity. It's a daily cycle of cooling and warming that transforms the landscape in the quiet hours when most of the world sleeps. Evaporation is happening everywhere around you, invisible and constant. Every body of water, from vast oceans to the smallest puddle, is constantly releasing water molecules into the air through evaporation. But water doesn't just evaporate from obvious sources. It rises from wet soil, from the surfaces of leaves through transpiration, from your own skin, and even from the moisture in your breath. This invisible process is one of the most important components of the water cycle, moving enormous amounts of water from the Earth's surface into the atmosphere where it can later return as precipitation. On a warm day, a large tree might transpire hundreds of liters of water into the atmosphere, contributing to the humidity and potentially influencing local weather patterns. Every plant, every body of water, and every moist surface is participating in this continuous exchange, adding moisture to the air that surrounds and sustains all life. Sublimation allows ice to disappear without melting. In the depths of winter, you might notice that snow and ice sometimes disappear even when temperatures never rise above freezing. This happens through sublimation, the direct transformation of ice crystals into water vapor without passing through the liquid phase. It's a slow, gentle process that occurs when the air is very dry, even in cold conditions. The ice crystals gradually release water molecules into the air, shrinking and eventually disappearing entirely. This is why clothes hung outside on a cold, dry winter day can actually dry, and why snow in some climates seems to evaporate rather than melt. Sublimation is also responsible for the gradual shrinking of ice cubes in your freezer over time. It's nature's way of moving water between its solid and gaseous states, bypassing the liquid phase entirely in a process that's both subtle and persistent. Air masses are like enormous, invisible weather personalities, stretching across hundreds or thousands of kilometers. Air masses are vast bodies of air that take on the characteristics of the regions where they form. An air mass that develops over a warm ocean becomes warm and moist, while one that forms over a cold landmass becomes cool and dry. These massive atmospheric personalities move slowly across continents and oceans, bringing their characteristics with them. When different air masses meet, they create weather fronts, the boundaries where different types of air interact and often produce clouds, precipitation, and changing weather conditions. The movement and interaction of air masses is like a slow-motion dance performed on a continental scale, with each air mass carrying the signature of its birthplace as it travels across the globe. Convection is the atmosphere's way of stirring itself. The uneven heating of the Earth's surface creates a constant process of air movement as warm air rises and cool air sinks. This convection process is responsible for much of the vertical movement in the atmosphere, creating the updrafts and downdrafts that form clouds, generate precipitation, and drive weather patterns. On a small scale, you can see convection at work in the shimmering air above hot pavement, or the steam rising from a warm cup of tea. On a larger scale, convection creates the towering cumulonimbus clouds of thunderstorms and the gentle circulation patterns that distribute heat throughout the atmosphere. It's a self-regulating system where temperature differences create motion, and that motion works to reduce the temperature differences, creating a dynamic balance that never quite reaches equilibrium. Temperature inversions create atmospheric puzzles where normal patterns reverse. Usually, air temperature decreases with altitude, creating the familiar pattern of cooler air higher up. But sometimes this normal arrangement flips, with warmer air sitting on top of cooler air near the ground. These temperature inversions can trap pollutants, moisture, and even sound waves close to the Earth's surface, creating unusual atmospheric conditions. Valley fog often forms and persists because of inversions, with cool air settling in low areas and warm air forming a lid above it. Inversions can also create acoustic anomalies, where sounds carry much farther than usual, or visual effects where distant objects appear unusually clear or distorted. These atmospheric reversals remind us that the atmosphere doesn't always follow the patterns we expect, sometimes creating its own unique local rules. Wind patterns create invisible rivers in the sky that flow in predictable currents. High above the weather you experience daily, the atmosphere organizes itself into vast circulation patterns that move air around the planet in enormous loops. These planetary-scale wind systems include the trade winds that blow steadily toward the equator, the westerlies that dominate mid-latitudes, and the polar easterlies that circulate around the Earth's poles. Between these major wind belts lie areas of relative calm, like the doldrums near the equator, where sailors once feared being stranded in windless seas. These global wind patterns are driven by the uneven heating of Earth's surface and the planet's rotation, creating a predictable framework that influences weather patterns across entire hemispheres. Understanding these invisible rivers of moving air helps explain why deserts form where they do, why some regions receive abundant rainfall while others remain dry, and how storms track across continents following these ancient atmospheric highways. Atmospheric rivers carry water vapor across oceans in narrow bands of moisture. Sometimes called rivers in the sky, these concentrated streams of water vapor flow through the atmosphere like terrestrial rivers flow across land. These atmospheric phenomena can be thousands of kilometers long, but only a few hundred kilometers wide, carrying water vapor from tropical regions toward the poles. When an atmospheric river encounters mountains or other geographic barriers, it's forced upward, cooling and releasing its moisture as precipitation. A single atmospheric river can carry more water than the Amazon River, though it's completely invisible to the naked eye. These moisture highways are responsible for much of the precipitation in certain regions, particularly along the west coasts of continents where mountains intercept the flowing water vapor. They represent the atmosphere's most efficient method of transporting water across vast distances, connecting weather patterns between distant parts of the globe. The boundary layer is where the Earth's surface whispers to the sky. In the lowest part of the atmosphere, roughly the first kilometer above ground, the moving air is directly influenced by friction with the Earth's surface. This boundary layer is where the smooth, fast-flowing air above meets the complex, textured world of forests, cities, mountains, and valleys below. Within this layer, wind speeds are slower and more turbulent, influenced by every hill, building, and tree. The thickness of the boundary layer changes throughout the day, growing taller as the sun heats the ground and creating rising thermals, then shrinking at night as the surface cools and the air becomes more stable. This is where most of the weather you directly experience occurs, where local geography shapes wind patterns, where morning fog forms, and where the character of the land below influences the behavior of the air above. It's the meeting place between the solid earth and the fluid atmosphere, a zone of constant interaction and exchange. Pressure gradients are the invisible forces that set air in motion. Air doesn't move randomly through the atmosphere. It flows from areas of higher pressure toward areas of lower pressure, following invisible slopes in the atmospheric pressure field. These pressure gradients can be gentle, creating light breezes that barely rustle leaves, or steep, generating powerful winds that reshape landscapes. The steeper the pressure gradient, the stronger the resulting wind. Weather maps show these pressure patterns as lines of equal pressure called isobars, creating topographic maps of the invisible hills and valleys of atmospheric pressure. When isobars are close together, indicating a steep pressure gradient, meteorologists expect strong winds. When they're far apart, the pressure gradient is gentle and winds are light. These pressure patterns are constantly shifting, creating the ever-changing dance of high and low pressure systems that determines your daily weather. Radiative cooling transforms clear nights into natural refrigerators. On cloudless nights, the Earth's surface radiates heat directly into space, with nothing to block or reflect that energy back downward. This process of radiative cooling can drop surface temperatures significantly, often creating the coolest temperatures of the entire day just before dawn. The effect is most pronounced on clear, calm nights when there are no clouds to act as a blanket and no wind to mix warmer air from above with the cooling air near the surface. This is why frost can form even when afternoon temperatures were quite warm, and why desert regions experience such dramatic temperature swings between day and night. The clear night sky becomes like an open window to the cold of space, allowing heat to escape upward and leaving the surface to cool through this silent, invisible process. Microclimates create weather neighborhoods within larger patterns. Even within a single city or region, subtle variations in geography, vegetation, and human-made structures create small-scale climate zones with their own weather characteristics. A park might be several degrees cooler than surrounding pavement due to the shade and moisture provided by trees. A south-facing hillside might be noticeably warmer and drier than the valley below. Urban areas often develop heat islands where concentrations of concrete and asphalt absorb and retain more heat than surrounding rural areas. These microclimates can be as small as a single garden or as large as a neighborhood, each creating its own subtle variations in temperature, humidity, and wind patterns. Understanding these local weather personalities helps explain why some spots always seem foggier, windier, or warmer than areas just a short distance away. Saturation is the invisible tipping point where air can hold no more water. Every parcel of air has a maximum capacity for water vapor, that depends on its temperature. Warm air can hold much more moisture than cool air. When air reaches its saturation point, it's like a saturated sponge that can't absorb another drop. Any additional moisture or any cooling of the air will cause water vapor to condense into visible droplets, forming clouds, fog, or dew. This saturation process is happening constantly in the atmosphere as air parcels rise and cool, warm and expand, or encounter surfaces at different temperatures. The relative humidity you hear in weather reports is actually a percentage of how close the air is to reaching this saturation point. Air at 100% humidity is fully saturated and ready to release its moisture at the slightest provocation, while air at lower humidity percentages can still absorb more water vapor before reaching its tipping point. Lenticular clouds form when air flows like water over invisible obstacles. When stable air encounters mountains or hills, it doesn't simply flow around them like you might expect. Instead, it behaves more like water flowing over a rock in a stream, creating standing waves on the downwind side of the obstacle. These atmospheric waves can extend for many kilometers downstream from the mountain, and when conditions are just right, they become visible as lenticular clouds. These lens-shaped or saucer-like clouds form at the crests of the invisible waves, where rising air cools and condenses, then dissipate at the troughs where air warms and the water vapor returns to invisible form. The clouds appear to hover motionless in the sky, but they're actually in constant motion, with new water vapor condensing on the upwind side while existing droplets evaporate on the downwind side. They mark the presence of powerful invisible waves in the atmosphere, smooth air currents that can extend high into the sky. Condensation nuclei are the tiny seeds around which clouds grow. Pure water vapor in the atmosphere would have great difficulty forming droplets on its own, even when the air becomes supersaturated. Instead, water vapor needs microscopic particles to serve as condensation nuclei, tiny surfaces around which water molecules can gather and form droplets. These particles can be specks of dust, pollen, salt from ocean spray, or even bacteria floating high in the atmosphere. Each cloud droplet begins its life wrapped around one of these invisible seeds. The size, shape, and chemical composition of condensation nuclei influence how clouds form and behave, affecting everything from droplet size to precipitation patterns. In very clean air with few particles, clouds may be reluctant to form even when humidity is high. In areas with more particles, clouds can form more readily, though too many particles can actually inhibit precipitation by creating so many tiny droplets that none grow large enough to fall as rain. Crepuscular rays are sunlight made visible by floating particles. Those dramatic beams of light that sometimes shine through breaks in clouds, creating what many people call God rays or sun pillars, are actually columns of illuminated air made visible by microscopic particles floating in the atmosphere. The light itself is always there, but you can only see it when dust, pollen, water droplets, or other tiny particles scatter the sunlight toward your eyes. These rays appear to diverge from the sun like the spokes of a giant wheel, though they're actually parallel beams of light made to appear divergent by perspective, much like railroad tracks seem to meet in the distance. The particles that make these light beams visible are the same ones that create spectacular sunrises and sunsets by scattering different wavelengths of light. When conditions are just right, these crepuscular rays can extend for kilometers, creating dramatic displays of visible sunlight streaming through the atmosphere. Advection is the atmosphere's way of sharing weather. When air masses move horizontally across the Earth's surface, they carry their temperature and moisture characteristics with them in a process called advection. This is how a warm, humid air mass from over the ocean can bring tropical conditions to areas far from the tropics, or how cold, dry air from polar regions can suddenly change the weather in temperate zones. Advection works on all scales, from the sea breeze that brings cooler air inland during hot summer afternoons, to the massive movement of air masses that can transport Arctic cold across entire continents. The process is usually gradual and steady rather than dramatic, like a slow tide of different air flowing across the landscape. Advection is responsible for many of the day-to-day weather changes you experience, as different types of air move over your location, carrying their own atmospheric personalities. Adiabatic processes control temperature changes in moving air. When air moves vertically in the atmosphere, either rising or sinking, its temperature changes in predictable ways that have nothing to do with gaining or losing heat from external sources. This happens because air pressure changes with altitude, and when air moves to regions of different pressure, it expands or compresses, which changes its temperature. Rising air expands and cools, while sinking air compresses and warms. This adiabatic cooling and warming is why mountaintops are cold even in summer, and why valleys can be surprisingly warm. The rate of temperature change is so consistent that meteorologists can predict exactly how much an air parcel will cool as it rises or warm as it sinks. These temperature changes drive many weather processes, from cloud formation to the development of precipitation, making adiabatic processes one of the fundamental engines of atmospheric behavior. Supercooled water droplets exist in a delicate state between liquid and solid. In clouds where temperatures are well below freezing, water droplets can remain liquid through a fascinating process that defies everyday experience. These supercooled droplets are in an unstable state, remaining liquid only because they lack the nuclei needed to begin the freezing process. They can exist at temperatures as low as -40 degrees Celsius, waiting for the right trigger to instantly transform into ice. When supercooled droplets encounter aircraft, tree branches, or other surfaces, they freeze immediately on contact, creating the dangerous ice accumulations known as rime ice or glaze ice. In clouds, supercooled droplets play a crucial role in precipitation formation, interacting with ice crystals in complex ways that determine whether precipitation falls as rain, snow, or something in between. These droplets represent water in a state of suspended animation, liquid in form but ready to transform into ice at the slightest provocation. The greenhouse effect is the atmosphere's way of keeping Earth warm. Certain gases in the atmosphere, including water vapor, carbon dioxide, and methane, have the remarkable ability to allow sunlight to pass through while trapping heat that radiates back from the Earth's surface. This natural greenhouse effect is what makes Earth warm enough to support liquid water and life as we know it. Without this atmospheric blanket, our planet would be a frozen world with an average temperature well below freezing. The process works because these greenhouse gases are transparent to the short wavelength sunlight coming from the sun, but absorb the longer wavelength heat radiation emitted by the Earth's surface. They then re-radiate this energy in all directions, including back toward Earth, creating a warming effect similar to the glass panels of a greenhouse. This natural process has kept Earth's temperature relatively stable throughout most of its history, creating the conditions that allow weather patterns and life itself to flourish. Orographic precipitation occurs when mountains force air upward into cooler regions. When moving air encounters a mountain range, it has no choice but to rise up and over the obstacle. As the air rises, it cools adiabatically, and if it contains sufficient moisture, clouds form and precipitation develops on the windward side of the mountains. This orographic lifting effect is why mountain ranges often have distinct wet and dry sides, with abundant precipitation on the side facing the prevailing winds and much drier conditions in the rain shadow on the leeward side. The process can create dramatic differences in precipitation over relatively short distances, with some mountain slopes receiving several meters of precipitation annually, while valleys just a few kilometers away remain arid. Orographic precipitation is responsible for many of the world's wettest locations, where mountains intercept moisture-laden air masses and wring the water from them through this simple process of forced ascent and cooling. Heat capacity differences between land and water create predictable wind patterns. Land surfaces heat up and cool down much more quickly than bodies of water, creating temperature differences that drive local wind systems. During the day, land becomes warmer than nearby water, causing air to rise over the land and draw cooler air in from over the water, creating a sea breeze or lake breeze. At night, the pattern reverses as the land cools more quickly than the water, creating a land breeze that flows from the cooler land toward the warmer water. These thermal circulation patterns are most noticeable near coasts, large lakes, and other significant bodies of water, where they can provide natural air conditioning during hot summer days and create predictable daily wind patterns. The same principle works on much larger scales, creating monsoon systems where seasonal temperature differences between continents and oceans drive massive seasonal wind patterns that bring wet and dry seasons to billions of people. Atmospheric tides are subtle pressure waves caused by the sun's heating. Just as the moon creates tides in Earth's oceans, the sun creates much smaller but measurable tides in the atmosphere through its daily heating cycle. These atmospheric tides cause air pressure to rise and fall in predictable patterns throughout the day, with the changes being most noticeable in tropical regions, where the sun's heating is most consistent. The pressure variations are tiny compared to the changes caused by weather systems, but sensitive instruments can detect them as regular oscillations that follow the sun's path across the sky. These atmospheric tides are evidence of the sun's influence on every aspect of Earth's atmosphere, creating subtle rhythms in air pressure that pulse like a planetary heartbeat driven by solar energy. The effect is so consistent that in some locations, you can predict the time of day just by measuring the atmospheric pressure as these solar-driven tides create their own quiet schedule in the invisible world of air pressure. Convective inhibition is the atmospheric lid that prevents storms from forming. Sometimes the atmosphere develops a layer structure where warm air sits above cooler air near the surface, creating what meteorologists call a capping inversion or convective inhibition. This invisible lid prevents surface air from rising freely, even when it contains plenty of moisture and energy. The result is often a buildup of atmospheric instability beneath the cap, like pressure building under a lid. If something eventually breaks through this inhibiting layer, perhaps through intense surface heating or an approaching weather front, the released energy can create explosive thunderstorm development, as all the pent-up instability is suddenly released. This is why some of the most severe thunderstorms develop during late afternoon or evening hours, when hours of solar heating have finally provided enough energy to break through the morning's stable layer structure. Convective inhibition demonstrates how the atmosphere can store energy and release it suddenly, creating periods of calm that are actually preparation for more dramatic weather. Virga creates phantom precipitation that never reaches thirsty ground. In arid regions, it's common to see gray streaks extending downward from clouds, like ghostly fingers reaching toward Earth. This virga represents precipitation that begins falling from clouds, but evaporates completely in the dry air below before it can reach the surface. The rain or snow falls into the unsaturated air beneath the cloud, where it gradually disappears, drawn back into the atmosphere as invisible water vapor. Sometimes virga creates dramatic visual displays, with curtains of precipitation creating shifting patterns as they encounter different air currents during their descent. The phenomenon is particularly common in desert climates, where hot, dry surface air can evaporate falling precipitation very efficiently. Virga represents the atmosphere's attempt to deliver moisture to dry landscapes, even when conditions aren't quite favorable for the water to complete its journey from cloud to ground. Downdrafts are invisible waterfalls of air that bring the sky to earth. In thunderstorms and other convective systems, what goes up must come down, and downdrafts are the atmosphere's way of returning air to the surface. These descending currents of air can be gentle and barely noticeable, or powerful enough to create dangerous wind shear conditions near airports. Downdrafts often carry cooler air from higher altitudes down to the surface, creating those sudden temperature drops you might feel when a storm approaches. They can also transport moisture, dust, and even the scent of rain from cloud level to ground level, which is why you might smell an approaching storm before you see it. In some cases, downdrafts become so strong they create microbursts, concentrated columns of descending air that spread out horizontally when they hit the ground, creating brief but intense wind patterns. These invisible air currents are the atmosphere's way of mixing layers that might otherwise remain separate, constantly stirring the lower atmosphere like a vast, gentle whisk. Sea breezes are nature's daily air conditioning system. Along coastlines around the world, a predictable and refreshing phenomenon occurs almost every sunny day. As the sun heats the land more quickly than it heats the adjacent ocean or lake, the air above the land becomes warmer and begins to rise. This creates a low-pressure area over the land that draws cooler air in from over the water. The result is a sea breeze that typically begins in late morning, strengthens during the afternoon, and fades as evening approaches. These coastal winds can penetrate many kilometers inland, bringing relief from hot summer temperatures and often triggering the formation of clouds and even brief showers. The sea breeze represents a perfect example of how temperature differences create motion in the atmosphere, generating its own local wind system that operates independently of larger weather patterns. It's a daily reminder of how the earth and sea work together to moderate temperatures and create comfortable conditions along coastlines. Cloud droplets are incredibly tiny spheres of almost pure water. A typical cloud droplet is only about 10 micrometers in diameter, roughly 1/10 the width of a human hair, and it takes millions of them to create a single raindrop. These microscopic spheres are so small, they can float indefinitely in even the gentlest air currents, suspended between gravity pulling them down and air resistance holding them up. Each droplet is essentially a perfect sphere, shaped by surface tension into the most efficient form possible. Despite their tiny size, cloud droplets are remarkably pure, containing almost nothing but water molecules arranged around a microscopic condensation nucleus. The process of cloud droplet formation is so delicate that slight changes in temperature, humidity, or air movement can cause them to evaporate back into invisible water vapor or grow through collision with other droplets. In their suspended state, these tiny spheres create the visible beauty of clouds while participating in the complex processes that eventually produce precipitation. Atmospheric stability determines whether air will rise smoothly or violently. The atmosphere's stability is like its temperament, determining whether it will remain calm and layered or become turbulent and active. When the air temperature decreases gradually with altitude, the atmosphere is stable, and any air that's displaced upward will tend to sink back to its original level. This creates smooth, layered cloud formations and generally calm weather conditions. But when temperature decreases rapidly with height, or when there are layers of warmer air above cooler air, the atmosphere becomes unstable. In unstable conditions, any air that starts rising will continue to rise, often accelerating upward and creating the towering cumulus clouds and thunderstorms associated with active weather. The degree of atmospheric stability changes throughout the day and season, influenced by solar heating, the movement of air masses, and topographic effects. Understanding stability helps meteorologists predict whether a day will remain peaceful and clear or develop into something more dramatic and energetic. Humidity affects more than just comfort. It influences the entire character of weather. The amount of water vapor in the air doesn't just determine how muggy or dry conditions feel. It fundamentally changes how the atmosphere behaves. Humid air is actually less dense than dry air at the same temperature, which affects how air masses move and interact. High humidity can inhibit evaporation from your skin, making warm temperatures feel much hotter, while low humidity enhances evaporation and can make you feel cool even in warm conditions. Humidity also affects visibility, with high moisture content in the air reducing how far you can see by scattering light. The water vapor in humid air stores enormous amounts of latent heat energy that gets released when the vapor condenses, which is why humid regions often experience more intense precipitation and storms. Even the speed of sound changes with humidity, traveling slightly faster through moist air than through dry air. Humidity is the invisible ingredient that flavors all other weather phenomena. Temperature inversions create atmospheric puzzles that reverse normal expectations. Normally, air temperature decreases steadily as you go higher in the atmosphere, but sometimes this pattern completely reverses, with warmer air sitting on top of cooler air near the surface. These inversions can trap pollutants, sounds, and even radio waves close to the ground, creating unusual atmospheric conditions that can persist for hours or even days. During strong inversions, you might hear distant sounds much more clearly than usual, or see objects on the horizon with unusual clarity as the layered air acts like a lens. Fog often forms and persists during inversions, with the cool surface air unable to mix with the warmer air above. Temperature inversions are most common during clear, calm nights when the ground radiates heat away rapidly, cooling the surface air while leaving the air above relatively warm. These atmospheric reversals remind us that the atmosphere doesn't always behave in predictable ways, sometimes creating its own unique local physics. Pressure systems are like vast, slow-moving weather personalities crossing the landscape. High-pressure systems bring generally calm, clear conditions as air sinks gently from above, suppressing cloud formation and creating stable weather patterns. The air in these systems spirals outward in a clockwise direction in the northern hemisphere, carrying their peaceful influence across hundreds of kilometers. Low-pressure systems have the opposite personality, with air spiraling inward and upward, often creating clouds, precipitation, and more active weather conditions. These systems move across continents like enormous atmospheric personalities, each bringing its own characteristic weather patterns. The boundaries between different pressure systems create fronts, zones where different air masses meet and often produce the most interesting and active weather. Understanding pressure systems helps explain why weather often comes in multi-day patterns, with several days of similar conditions, followed by changes as new pressure systems move through the region. Sublimation allows snow to disappear without creating puddles. In cold, dry conditions, snow and ice can vanish directly into the air without ever becoming liquid water. This process of sublimation happens when ice crystals release water molecules directly into the atmosphere, bypassing the melting phase entirely. It's particularly noticeable in environments with low humidity and steady airflow, where snow seems to evaporate rather than melt. The process is slow and gentle, often creating interesting patterns, as some areas of a snow surface sublime faster than others due to slight differences in wind exposure or solar radiation. Sublimation is also responsible for the gradual disappearance of frost from surfaces even when temperatures remain below freezing, and for the way ice cubes slowly shrink in your freezer over time. It's nature's way of moving water between its solid and gaseous phases without the intermediate liquid step. A quiet process that can make winter precipitation disappear as mysteriously as it arrived. Supercells are nature's most perfectly organized storms. These rare but magnificent thunderstorms develop a rotating structure that can persist for hours, creating some of the most severe weather conditions on Earth. Unlike ordinary thunderstorms that build upward and then collapse, supercells maintain their structure through a delicate balance of updrafts and downdraft, arranged around a rotating column of air called a mesocyclone. This rotation gives the storm its longevity and intensity, allowing it to produce large hail, damaging winds, and sometimes tornadoes. The rotating structure also gives supercells their distinctive appearance on weather radar, showing up as hook-shaped echoes that meteorologists can identify from great distances. Despite their potential for destruction, supercells represent some of the most beautiful and well-organized phenomena in the atmosphere, with spiral structures that can tower more than 15 kilometers into the sky while maintaining their coherent form for many hours. Evapotranspiration is the combined breathing of earth and plants. This process combines evaporation from soil and water surfaces with transpiration from plants, creating a continuous flow of water vapor from the Earth's surface into the atmosphere. During transpiration, plants draw water up through their roots and release it through tiny pores in their leaves, effectively breathing moisture into the air. A large tree can transpire hundreds of liters of water per day, contributing significantly to local humidity levels. The combined effect of evapotranspiration helps cool the surface through the energy required to change liquid water into vapor, which is why forested areas often feel cooler and more humid than nearby cleared land. This process also helps explain why deforestation can affect local weather patterns, as the removal of trees reduces the amount of moisture being added to the atmosphere. Evapotranspiration represents the active participation of living systems in the water cycle, with every plant serving as a tiny weather-making machine. Convergence zones are where different air masses meet and create weather. These invisible boundaries in this atmosphere occur where winds flowing from different directions come together, forcing air to rise and often triggering cloud formation and precipitation. Convergence can happen on scales ranging from local sea breeze fronts to massive intertropical convergence zones that circle the globe near the equator. When air masses with different temperatures, humidity levels, or wind directions meet, they don't mix immediately. Instead, they create distinct boundaries where rising air can produce clouds and storms. Some convergence zones are semi-permanent features of global atmospheric circulation, while others form and dissipate daily as local heating and cooling patterns change. These meeting places of different air streams are often the birthplaces of weather systems, where the atmosphere's tendency toward motion and change becomes visible in the clouds and precipitation that form along these invisible seams in the sky. Radiational cooling turns clear nights into natural refrigeration systems. When the sun sets and solar heating stops, the Earth's surface continues to radiate heat upward into space. On clear nights with minimal cloud cover, this heat escapes freely, causing surface temperatures to drop steadily through the night. The cooling effect is most pronounced just before dawn, when the accumulated heat loss reaches its maximum. This process can create surprisingly large temperature differences between day and night, particularly in desert regions where dry air and clear skies allow maximum heat loss. Radiational cooling is also responsible for the formation of dew and frost, as surfaces cool below the dew point temperature of the surrounding air. The process demonstrates how the Earth maintains its energy balance, radiating away the heat it received during daylight hours, and preparing for the next cycle of solar heating. Isentropic surfaces are invisible highways in the atmosphere where air masses prefer to travel. These theoretical surfaces connect points of equal potential temperature, creating pathways that air naturally follows as it moves through the three-dimensional atmosphere. Air tends to flow along these surfaces rather than across them, much like water follows the contours of a landscape. Meteorologists use isentropic analysis to track the movement of air masses and predict where weather systems will develop or move. These surfaces can slope gently or steeply through the atmosphere, and they often provide insight into the large-scale patterns that govern weather behavior. While invisible to the casual observer, isentropic surfaces represent the preferred pathways of atmospheric motion, the routes that air masses naturally follow as they respond to the forces of pressure, temperature, and the Earth's rotation. Understanding these invisible highways helps explain why weather systems often follow predictable paths and why certain regions experience similar weather patterns repeatedly. Valley breezes and mountain breezes create daily wind cycles in mountainous terrain. During the day, valley floors and mountain slopes heat up at different rates, creating temperature differences that drive local wind patterns. Warm air rises from heated valley floors, drawing cooler air down from the mountains to replace it, creating valley breezes that flow upslope during daylight hours. At night, the pattern reverses as mountain slopes cool rapidly through radiational cooling, creating dense, cool air that flows downslope into valleys as mountain breezes. These local wind systems can be surprisingly strong and consistent, creating their own daily weather patterns independent of larger-scale atmospheric circulation. The interaction between valley and mountain breezes can also influence cloud formation, with upslope winds during the day often triggering afternoon thunderstorms over mountain peaks, while downslope winds at night can clear out clouds and create calm conditions in valleys. These thermal circulation patterns demonstrate how topography creates its own local weather systems through the simple physics of differential heating and cooling. Cyclogenesis is the quiet birth of storm systems from atmospheric instability. This process begins when small disturbances in the atmosphere encounter the right combination of temperature contrasts, moisture, and wind patterns. What starts as a minor ripple in the flow of air can gradually intensify, drawing energy from temperature differences between air masses and organizing itself into a rotating low-pressure system. The process is usually slow and methodical, taking place over several days as the developing system gathers strength and structure. Cyclogenesis often occurs along frontal boundaries where warm and cold air masses meet, or in regions where upper-level atmospheric patterns create favorable conditions for surface development. The resulting storms can range from gentle rain systems that bring needed moisture to agricultural regions, to more intense cyclones that reshape weather patterns across entire continents. Each storm system that develops through cyclogenesis carries the signature of the atmospheric conditions that created it, becoming a unique expression of the forces that drive weather. Anticyclones are the atmosphere's zones of calm stability and clear skies. These high-pressure systems represent areas where air is gently sinking from higher altitudes, compressing and warming as it descends. This subsiding motion suppresses cloud formation and creates the stable, fair weather conditions that anticyclones are known for. The air in these systems spirals outward from the center, creating a clockwise circulation in the northern hemisphere that can extend for hundreds of kilometers. Anticyclones often persist for days or even weeks, creating extended periods of settled weather with light winds and clear skies. They act like atmospheric anchors, slowing the movement of other weather systems and creating blocking patterns that can redirect storm tracks around their influence. 2. The gentle, persistent nature of anticyclones makes them responsible for many of the most pleasant weather periods. When high pressure creates those perfect days with unlimited visibility, comfortable temperatures, and the kind of stable conditions that make you want to spend time outdoors. Mesoscale convective systems organize individual thunderstorms into larger weather patterns. Sometimes, instead of forming as isolated cells, thunderstorms organize themselves into larger, more complex systems that can cover areas the size of entire states. These mesoscale convective systems develop their own circulation patterns and can persist for many hours, often traveling hundreds of kilometers while maintaining their organized structure. The systems typically form during overnight hours when upper-level atmospheric patterns provide the right combination of wind shear and instability. They can produce widespread areas of beneficial rainfall, but also create hazardous conditions, including damaging winds, large hail, and flash flooding. The organized nature of these systems allows them to be more efficient at producing precipitation than isolated storms, often delivering significant rainfall to drought-affected regions. Mesoscale convective systems represent the atmosphere's ability to organize chaos into structured patterns, creating weather phenomena that are larger than individual storms, but smaller than major frontal systems. Atmospheric waves propagate through the sky like ripples on an invisible pond. These waves form when stable air encounters obstacles or disturbances, creating oscillations that can travel for hundreds of kilometers through the atmosphere. Mountain waves are perhaps the most familiar type, forming when wind flows over mountain ranges and creating standing wave patterns on the downwind side. But atmospheric waves can also be generated by thunderstorms, jet streams, or even the heating and cooling cycles of day and night. These waves are usually invisible to the naked eye, but they can sometimes be revealed by the formation of lenticular clouds at their crests, or by the turbulence they create for aircraft. Atmospheric waves transport energy and momentum through the atmosphere, influencing weather patterns far from their source. They represent the atmosphere's way of responding to disturbances, creating organized patterns of motion that can persist long after the original disturbance has passed. Convergence zones create invisible seams in the atmosphere where weather is born. These boundaries form wherever winds from different directions meet, forcing air to rise and often triggering the development of clouds and precipitation. The convergence can be subtle, with gentle air currents meeting and gradually ascending, or dramatic, with strong winds colliding and creating rapid upward motion. Some convergent zones are permanent features of global circulation, like the intertropical convergence zone that circles the Earth near the equator. Others are temporary, forming and dissipating as local heating patterns, or passing weather systems create temporary wind patterns. Sea breeze convergence zones form along coastlines where land and sea breezes meet, often creating afternoon thunderstorms, storms. Dryline convergence zones develop where moist and dry air masses meet, creating some of the most favorable conditions for severe thunderstorm development. These invisible boundaries represent the atmosphere's tendency to create order from chaos, organizing seemingly random air movements into predictable patterns. Backing and veering winds tell stories about approaching weather changes. When winds gradually shift direction over time, they're responding to changes in the pressure patterns and temperature gradients that drive atmospheric circulation. Backing winds, which shift counterclockwise over time, often indicate the approach of a warm front or low-pressure system. Veering winds, which shift clockwise, typically suggest the passage of a cold front or the approach of high pressure. These wind shifts can be subtle, changing just a few degrees per hour, but they provide valuable clues about how weather patterns are evolving. Pilots and sailors have long used wind direction changes to anticipate weather changes, and meteorologists incorporate wind shift patterns into their forecasting process. The changing wind directions reflect the three-dimensional structure of the atmosphere, ossphere, where different layers of air may be moving in different directions as weather systems approach and pass. Diabatic heating processes add and remove energy from the atmosphere in ways that drive weather systems. Unlike the adiabatic processes that simply redistribute existing energy as air moves vertically, diabatic processes actually change the total energy content of air masses. Latent heating occurs when water vapor condenses into droplets or ice crystals, releasing the energy that was stored when the water originally evaporated. This process powers thunderstorms and hurricanes, providing the energy that drives their intense circulation patterns. Radiational heating and cooling occur as surfaces absorb solar energy during the day and radiate it away at night. Sensible heating transfers energy directly from warm surfaces to the air above them, while evapotranspiration removes energy from the surface as liquid water changes to vapor. These diabatic processes are the atmosphere's energy sources and sinks, the mechanisms by which weather systems gain and lose the energy that drives their motion and intensity. Potential temperature is the atmosphere's way of revealing hidden energy relationships. This concept represents the temperature an air parcel would have if it were moved adiabatically to a standard pressure level, removing the effects of pressure differences and revealing the true thermal energy content of different air masses. Air masses with the same potential temperature will have the same density when brought to the same pressure level, even if their actual temperatures are quite different due to being at different altitudes. Meteorologists use potential temperature to track air masses as they move through the atmosphere, since potential temperature remains constant as air moves adiabatically. This makes it easier to follow the paths of air masses and understand how they interact with each other. Potential temperature also helps identify atmospheric stability, since air will only rise if it's warmer than its surroundings when compared at the same potential temperature level. Equivalent potential temperature incorporates the hidden energy of water vapor. This advanced meteorological concept takes potential temperature one step further by including the latent heat energy stored in water vapor. It represents the temperature an air parcel would reach if all its water vapor were condensed out, releasing the latent heat, and then the parcel were brought adiabatically to a standard pressure level. Equivalent potential temperature is conserved during both dry and moist adiabatic processes, making it an excellent tracer for following air masses through complex atmospheric processes. It helps meteorologists identify the potential for thunderstorm development, since air with high equivalent potential temperature contains large amounts of energy that can be released through convection. This parameter is particularly useful in tropical meteorology, where the energy content of moist air masses plays a crucial role in the development of hurricanes and other tropical weather systems. Thermal wind relationships explain why upper-level wind patterns differ from surface winds. The thermal wind isn't actually a wind you can feel. It's a theoretical concept that describes how wind speed and direction change with altitude due to temperature gradients. In regions where there's a strong temperature contrast, such as along the boundary between warm and cold air masses, the wind speed increases with altitude and the wind direction shifts in a predictable way. This relationship helps explain why jet streams exist at high altitudes, where large temperature contrasts between tropical and polar air masses create fast-moving rivers of air. The thermal wind relationship also explains why surface low-pressure systems often tilt with height, leaning in the direction of the thermal wind. Understanding these relationships helps meteorologists interpret upper air data and predict how surface weather systems will move and evolve. Quasi-geostrophic theory describes the large-scale balance of forces in the atmosphere. This elegant framework explains how the atmosphere maintains approximate balance between the Coriolis force and pressure gradient forces, while allowing for the slow evolution of weather systems. Under quasi-geostrophic conditions, the atmosphere behaves in predictable ways, with air flowing parallel to lines of constant pressure and weather systems moving in response to upper-level divergence and convergence patterns. This theory provides the foundation for understanding how large-scale weather patterns develop and move, explaining why low-pressure systems typically move from west to east in the mid-latitudes, and how upper-level troughs and ridges influence surface weather. The quasi-geostrophic framework, RK, allows meteorologists to use simplified equations to predict weather system movement and intensity, providing a powerful tool for understanding atmospheric dynamics. Potential vorticity is a quantity that helps meteorologists track atmospheric disturbances. This parameter combines information about the rotation and stratification of the atmosphere into a single value that remains nearly constant as air moves through the atmosphere. High values of potential vorticity are associated with weather disturbances and can be used to track the movement of storms and other atmospheric features. The conservation of potential vorticity helps explain how atmospheric disturbances can maintain their identity as they move across continents and oceans. It also provides insight into how upper-level atmospheric patterns influence surface weather, since changes in potential vorticity at high altitudes can trigger the development of surface weather systems. This concept presents one of the atmosphere's fundamental conservation laws, providing a powerful tool for understanding and predicting weather system behavior. Boundary layer processes connect the Earth's surface to the free atmosphere above. The planetary boundary layer is the lowest part of the atmosphere, where the direct effects of the surface create turbulence and mixing that wouldn't occur in the smooth flow of the free atmosphere above. During the day, solar heating creates convective mixing that can extend the boundary layer to heights of several kilometers. At night, radiational cooling creates a shallow, stable boundary layer that suppresses vertical mixing. The depth and characteristics of the boundary layer influence many weather phenomena, from fog formation to the development of thunderstorms. Understanding boundary layer processes is crucial for predicting surface weather conditions, since this is where most of the weather we experience directly occurs. The boundary layer is where the atmosphere and the Earth's surface communicate, exchanging energy, moisture, and momentum in complex ways that influence weather patterns. Rossby waves are planetary-scale undulations in the jet stream that influence weather patterns across hemispheres. These massive atmospheric waves form due to the conservation of potential vorticity as air moves over the rotating Earth, creating the familiar pattern of troughs and ridges seen on upper-level weather maps. Rossby waves propagate slowly eastward around the hemisphere, typically completing a circuit in several weeks. The position and amplitude of these waves determine the general weather patterns experienced by different regions, influencing whether areas experience warm or cool conditions, wet or dry periods. When Rossby waves become particularly amplified, they can create blocking patterns that cause weather systems to stall, leading to prolonged periods of unusual weather as heat waves, cold snaps, or extended precipitation events. These planetary waves represent the atmosphere's response to the Earth's rotation and the uneven heating between tropical and polar regions, creating a global framework within which smaller-scale weather systems develop and move. Ensemble forecasting reveals the atmosphere's inherent uncertainty by running multiple weather models with slightly different initial conditions. Rather than producing a single prediction, meteorologists create dozens of parallel forecasts, each beginning with tiny variations in temperature, pressure, or wind speed measurements. These small differences, often smaller than the precision of observing instruments, can lead to dramatically different weather outcomes several days later, illustrating the chaotic nature of atmospheric systems. The ensemble approach acknowledges that perfect prediction is impossible, while still providing valuable guidance about probable weather scenarios. When all ensemble members agree on a forecast, confidence is high. When they diverge widely, it signals that conditions are particularly uncertain. This probabilistic approach to weather prediction represents a more honest and scientifically rigorous way of communicating atmospheric uncertainty, recognizing that the atmosphere's complexity makes deterministic prediction beyond a certain time limit fundamentally impossible. Mesocyclones are rotating columns of air within supercell thunderstorms that can persist for hours while maintaining their coherent structure. These vertical vortices form when horizontal wind shear is tilted into the vertical by strong updrafts, creating a rotating cylinder of air that extends through much of the storm's depth. The mesocyclone gives supercells their longevity and intensity, allowing them to maintain themselves far longer than ordinary thunderstorms. The rotation also creates a distinctive hook-shaped appearance on weather radar that can be detected from hundreds of kilometers away. While not all mesocyclones produce tornadoes, they represent the atmospheric conditions most favorable for tornado development. The rotating structure helps organize the storm's updrafts and downdrafts in ways that enhance its strength and persistence. Mesocyclones demonstrate the atmosphere's ability to create ordered, rotating structures from seemingly chaotic convective processes, transforming ordinary thunderstorm updrafts into long-lived, rotating systems. Atmospheric rivers transport water vapor across ocean basins in narrow corridors of concentrated moisture. These phenomena can extend for thousands of kilometers while remaining only a few hundred kilometers wide, creating invisible highways of water vapor that connect tropical moisture sources to mid-latitude precipitation areas. A single atmospheric river can transport more water than the Amazon River, though the moisture remains completely invisible as it flows through the sky. When these moisture plumes encounter mountains or other lifting mechanisms, they can produce enormous amounts of precipitation in relatively short periods. The west coasts of continents are particularly susceptible to atmospheric river events, which can bring both beneficial drought relief and destructive flooding. These rivers in the sky represent one of the atmosphere's most efficient mechanisms for transporting water vapor across vast distances, connecting weather patterns between widely separated regions of the globe. Kelvin-Helmholtz instability creates rolling cloud formations that look like ocean waves in the sky. This phenomenon occurs when there's a strong speed difference between two layers of air moving in the same direction, creating a shearing motion that generates distinctive wave-like cloud patterns. The instability manifests as a series of curling, spiral formations that resemble breaking waves, complete with foam-like wisps of cloud at their crests. These formations are relatively rare and short-lived, typically lasting only minutes before the turbulent mixing destroys the organized wave pattern. Kelvin-Helmholtz clouds often form near mountain ranges where wind shear is enhanced by topographic effects, or at the boundaries between different air masses moving at different speeds. The phenomenon demonstrates how the atmosphere responds to velocity differences by creating organized turbulent structures, turning invisible wind shear into visible artistic patterns that grace the sky with their brief, wave-like beauty. Gravity waves propagate through the atmosphere like ripples spreading from a disturbance in a pond. These waves form when stable air is displaced vertically and then oscillates around its equilibrium position, creating wave motions that can travel for hundreds of kilometers through the atmosphere. Unlike sound waves, gravity waves are restored by buoyancy forces, with displaced air parcels bobbing up and down like corks on water. These waves can be generated by thunderstorms, flow over mountains, or other atmospheric disturbances, and they transport energy and momentum far from their source. Gravity waves often remain invisible, but sometimes they can be revealed by wave-like cloud patterns or by the turbulence they create when they break like ocean waves. They play important roles in atmospheric circulation, helping to transport energy between different layers of the atmosphere and influencing the development of weather systems far from where they originated. Lid strength determines whether atmospheric instability will be released explosively or suppressed entirely. The atmosphere often develops layered structures where warm air sits above cooler air, creating an invisible ceiling that prevents surface air from rising freely. The strength of this lid, or capping inversion, determines whether building instability will eventually break through in explosive thunderstorm development or remain suppressed beneath the stable layer. A strong lid can hold back tremendous amounts of atmospheric energy, like a pressure cooker building steam. When something finally breaks through this atmospheric ceiling, the released energy can create some of the most intense thunderstorms and severe weather events. The timing and location of lid erosion often determines when and where severe weather will develop, making the monitoring of these invisible atmospheric barriers crucial for accurate severe weather forecasting. Streamlines reveal the invisible architecture of wind flow patterns throughout the atmosphere. These imaginary lines show the instantaneous direction of air movement at every point, creating flowing patterns that reveal how the atmosphere organizes its motion. Streamlines can show converging flows that create rising motion and diverging flows that create sinking motion, helping meteorologists identify areas where weather systems are likely to develop or dissipate. The patterns can be smooth and laminar in stable conditions or chaotic and turbulent when the atmosphere is disturbed. Analyzing streamline patterns at different altitudes reveals the three-dimensional structure of atmospheric flow, showing how surface weather patterns relate to upper-level wind systems. These invisible roadmaps of air movement help explain why weather systems move along certain paths and how different layers of the atmosphere interact to create the complex patterns we observe as weather. Diabatic heating from condensation powers the most intense atmospheric circulation systems. When water vapor condenses into droplets or ice crystals, it releases latent heat energy that was stored during the original evaporation process. This energy release can be enormous in systems with abundant moisture, providing the fuel that drives hurricanes, thunderstorms, and other intense weather phenomena. The heating is concentrated in the middle levels of the atmosphere where most condensation occurs, creating temperature patterns that enhance circulation and draw in more moist air to continue the process. This positive feedback mechanism allows some weather systems to become self-sustaining and even intensifying, as long as they have access to moisture and favorable atmospheric conditions. The conversion of latent heat energy through condensation represents one of the atmosphere's most powerful energy sources, capable of creating circulation systems with wind speeds that exceed anything produced by other atmospheric processes. Vorticity measures the local rotation and shear in atmospheric flow patterns. This fundamental quantity describes how much the air is spinning or shearing at any given point, providing insight into the rotational characteristics of weather systems. Areas of positive vorticity are associated with cyclonic rotation and often coincide with the development of low-pressure systems and storms. Vorticity can be created by the curvature of flow patterns, by speed differences across a region, or by the Coriolis effect on a rotating planet. The conservation and advection of vorticity help explain how atmospheric disturbances move and evolve, providing meteorologists with tools for predicting weather system development and movement. Changes in vorticity patterns often precede the development of new weather systems, making vorticity analysis a valuable technique for identifying areas where storms are likely to form or intensify. Tropopause dynamics influence how weather systems interact with the stratosphere above. The tropopause represents the boundary between the turbulent troposphere where weather occurs and the stable stratosphere above, typically located at altitudes of 8 to 15 kilometers, depending on latitude and season. This boundary isn't fixed, but undulates like a flexible membrane, rising and falling in response to the weather systems below. Strong low-pressure systems can push the tropopause upward, while high-pressure areas allow it to sink lower. The height and temperature of the tropopause influence jet stream behavior and can affect how weather systems develop and move. Exchange processes across the tropopause help transport water vapor and other trace gases between the troposphere and stratosphere, influencing both weather patterns and atmospheric chemistry. Understanding tropopause behavior is crucial for predicting how intense weather systems will evolve and how they might interact with the upper atmosphere. Clear air turbulence forms in regions of strong wind shear even without visible weather. This phenomenon occurs when layers of air moving at different speeds create invisible zones of chaotic motion that can extend for kilometers through apparently calm skies. The turbulence typically develops near jet streams, in mountain wave systems, or along the edges of thunderstorms where wind speeds change rapidly over short distances. While invisible to the naked eye and often undetectable by weather radar, clear air turbulence can create significant hazards for aviation and uncomfortable conditions for passengers. The turbulent regions can be remarkably persistent, maintaining their chaotic structure for hours as they move with the general atmospheric flow. Predicting clear air turbulence requires sophisticated analysis of wind shear patterns and atmospheric stability, since traditional weather observation methods often can't detect these invisible zones of atmospheric chaos. Symmetric instability creates slantwise convection in winter storms and other weather systems. Unlike ordinary convection, where air rises vertically, symmetric instability allows air parcels to rise along slanted paths that are neither purely horizontal nor purely vertical. This process often occurs in winter storms, where strong temperature gradients and wind shear create conditions favorable for slantwise motion. The resulting convection can produce heavy snow bands and intense precipitation rates, even when the atmosphere isn't unstable to purely vertical motion. Symmetric instability helps explain how some winter storms can produce surprisingly intense precipitation, and how narrow bands of heavy snow can develop within larger storm systems. The slanted nature of the convection creates circulation patterns that are different from those in ordinary thunderstorms, often producing stratified precipitation structures with embedded areas of enhanced intensity. Conditional instability exists when the atmosphere is stable for unsaturated air, but unstable for saturated air. This common atmospheric condition means that air parcels will remain stable as long as they don't reach saturation. But once they become saturated and begin forming clouds, they can rise rapidly and create convective storms. The atmosphere achieves this dual personality through its vertical temperature structure, which allows it to suppress small disturbances while still permitting larger disturbances to grow explosively once they overcome the initial barrier. Conditional instability explains why some days can seem perfectly calm until a trigger mechanism initiates cloud formation, after which thunderstorms develop rapidly. The condition is widespread during summer months, when solar heating creates favorable temperature profiles, but moisture and lifting mechanisms are needed to release this instability and transform calm conditions into active weather. Convective available potential energy quantifies the amount of instability energy available for thunderstorm development. This parameter measures how much kinetic energy an air parcel would gain if it were lifted from the surface to the top of the atmosphere, representing the fuel available for convective storms. Higher values of convective available potential energy indicate greater potential for intense thunderstorm development, with very high values associated with severe weather events. The energy calculation takes into account both the temperature and moisture content of the air, since both contribute to the buoyancy forces that drive convection. Meteorologists use this parameter to assess thunderstorm potential and to forecast the likely intensity of convective activity. The spatial and temporal distribution of convective available potential energy helps explain why some regions are more prone to thunderstorm development and why storm intensity can vary dramatically over relatively short distances. And now, as the final whispers of atmospheric wisdom settle around you like morning mist, we've journeyed together through the gentle mysteries that surround us every moment. From the crystalline architecture of snowflakes to the invisible rivers of water vapor flowing thousands of kilometers above. From the quiet breathing of pressure systems to the delicate dance of molecules in every breath you take, we've discovered that weather isn't just something that happens to us, but something we're intimately connected to, part of the vast breathing system that envelops our entire planet. The atmosphere holds you gently, pressing against your skin, flowing through your lungs, connecting you to distant storms and faraway places through currents of air that circle the globe. Even now, as your thoughts grow soft and your breathing slows, these invisible processes continue their ancient rhythms around you. If these peaceful explorations have brought you comfort or helped carry you towards sleep, remember that tomorrow's weather will bring new quiet wonders, new gentle secrets waiting to be discovered in every cloud and breeze. Sweet dreams, and may your rest be as calm as a stable atmosphere under starlight.